So let's do another example. This one has proportions again. And now it's a one-tailed test. So it's a one-sided test. The alternative will be one-sided. The null is always something equal to some number, some parameter equal to number. The alternative is parameter between and something like less than, greater than, or not equal to, and the same number. So we're going to be doing it. We're going to be doing that. So it's typically 22% of students get an A in a university stats class. In an online class, 82 out of 400 earned an A. So 82 out of 400 is 0.205. So 20% of 400 is 80, and then 0.005 will give you more, 2 more, to make 82, so 0.205. Or just 82 divided by 400 is 0.205. So that's less than 22%, but is it far enough away that we can claim that something different is happening in this online class compared to the usual case of 22%? So here we go. The null hypothesis is 22%. The alternative is, I think maybe it's less than 22%, but is it? And then we compute z. Here's z that we use. P hat minus p, square root of p, 1 minus p over n. We put 0.205 for p hat, 0.22 for p. It goes here and here. 1 minus 0.22 is 0.78. Yes, it is. N was 400. 82 of 400. There it is. I get minus 0.7242. Now, we've been around a little while, and we know to reject the null hypothesis, that thing has to be bigger or smaller than something like 2 or minus 2. It isn't, so we're not going to reject the null hypothesis. But let's just see exactly how it looks. So in the classical approach, we look for unusual values of z favoring the alternative. The ones we would use would be z's less than minus 1.645. Because the one-tailed test, so these kinds of things that would happen by accident, we want that to be around 5%. Since it's only one-sided, the z we can use is negative 1.645 to fall in that region. So we'll reject the null hypothesis if our z is smaller than negative 1.645. Of course, we got minus 0.72, which is here. It's not in that region. And so we'll fail to reject the null hypothesis. So as far as we know, it looks like p could easily be 0.22. So we would say values of the test statistic can easily be the value, maybe? The value test that could easily be caused by random variation. So we know these values near 0 can be thought to be just random, and it'll have to be pretty far away not to be random. It isn't far away, so we can't claim anything happened. It could just be random variation, not because the actual proportion long term is less than 22%. This 82 is not far enough away from 400, is what we're saying. The p-value approach should have the same kind of outcome and use some of the same kinds of thinking. You take the test statistic value and you find the tail probability. The tail probability comes out to be 2358. So if we go to 0.72 here and we shade this direction, then we get 0.2358. 0.005 is there. You have to come over quite a ways to get to 358. You're too close to 0 to be considered a contender for rejecting the null hypothesis. But instead of doing that, we just compare the p-value to 0.05. Similar thinking, it's just we don't have to know what the test statistic value really means. So we got the 2305, we compared to 0.05, but this is not less than 0.05. So we fail to reject the null hypothesis at the 0.05 level. So those are the two approaches with one-sided and two-sided tests for proportions, either by looking at the test statistic value or looking at the proportion value, comparing it to how far away from the center you'd have to be considered unusual. And then when you don't break that boundary, you don't reject. Over here, computing the p-value by finding the tail probability associated with the value of z that we got. has to be less than 0.05. If it isn't, we fail to reject the null hypothesis. And you can see how those two ways of thinking are parallel and almost identical. And we give you both in this class because you never know when you're reading some research, you may not know exactly the details of the test, but you'll understand what the p-value is, and that lets you understand what you should conclude. And you might differ with what the authors say, because sometimes the authors will make false claims, but they'll give you the correct value of the p-value, because that's what comes out of software, and you can just look at it and go, hey, I think you guys are trying to scam me on this one. And so I'm not trying to scam you on this, I'm just trying to finish this section, and I think we just did it.